Hello, welcome to the lecture 2 of the course on protein engineering. And here in this lecture, we will proceed from the earlier lecture where we saw how the changes in the R group of an amino acid differentiate each of these amino acids as individual amino acids. Here in this lecture, we will see how these amino acids singularly in various combinations form a protein. The linear arrangement of amino acids, or as we call it here as residues, in a specific order are called the primary structure of a protein. So the sequence in which the amino acids are arranged is very specific, and this is like a signature for a protein. Here we see how does this arrangement happen. The amino acids individually, as in this case residue N and N plus 1, that is the first amino acid and the second amino acid, have to interact with each other so as to form a sequence N followed by N plus 1. For this, the amino acids interact very specifically, like the carboxylic group of nth amino acid and the amino group of the N plus 1th amino acid interact at their OH and hydrogen atom respectively to form a bond that is called the peptide bond. During this process, there is a release of water molecule, and hence the bond formation reaction is called a condensation reaction, where residue N and residue N plus 1 can form a peptide. It is called a dipeptide because there are two amino acids that compose of this peptide. So for a dipeptide, there will be one peptide bond. For a tripeptide, there will be two peptide bonds. The peptide bond is having a peculiar character, though it looks like a single bond. As you could have seen in the earlier slide, the carbons saturation has attained, and the amino groups N has also been saturated by the bonds that are formed. That is just like a single bond between carbon and nitrogen. But here exists a peculiar character where it is not having a bond distance that is equivalent to neither the carbon-nitrogen single bond nor carbon-nitrogen double bond, as you can see in the bottom of the slide, but it is having something as an average that is in between these two bonds. This is why this particular bond is considered to be a partial double bond, that is partly single and partly double. Here a thing to notice is how come this particular bond became a partial double bond. What does it mean? As you can see, the carbon and nitrogen are connected to an oxygen and hydrogen group respectively, which tend to have a partial negative and a partial positive charge. A partial negative means it can have the ability to donate an electron at some point of time, and also a partial positive charge means it can have a ability to attract an electron at some point of time. Hence, there is a movement of electron across this O and H through the carbon and nitrogen, and hence the carbon and nitrogen tend to be like a partial double bond. As you can see, there is a slight difference in the representation of carbon and nitrogen and the peptide bond that is being formed, with the oxygen and hydrogen facing the opposite direction in this representation. This is what we call as a trans conformation. In trans conformation, you see the groups that are on either side of the bond formation be on the opposite direction. This is as favorable as the earlier depiction, as you have seen in the previous slide, where the oxygen and hydrogen and also the R group of the N+1 residue were all in the same side as the nth residue. But this is being a less preferred conformation because of the steric clashes that happen because of the existence of the R group with the subsequent molecules that interact with them. That is the non-bonding atoms that are found, that is called the H and the O, and also the subsequent R. These hinder the presence of each other, thereby the trans conformation becomes the most feasible or favored conformation for a peptide bond forming atoms. This peptide bond has another character called the planar character. Otherwise, we can say that the atoms that form a chain, just like you have seen on the left hand side with the H and the ending with the OH on the right hand side, you see a sequence of bonds. These bonds necessarily do not exist as you have seen here in the depiction as a linear form, as if they are in the same plane, but they tend to be up and down and up and down, or you can call them as puckered. The general notation will be that each of these atoms will be in a different plane. But here in a peptide bond, the atoms starting from C alpha to the peptide bond forming carbon atom and the peptide bond forming nitrogen atom and their respective connected atoms and the C alpha of the N+1 residue all form a same plane. This structure actually favors the partial double bond that you have seen in the earlier slide, because the oxygen transport from the partially negatively charged oxygen atom to the hydrogen, which has a partial positive charge, happens simultaneously all the time. Means the electron can be either in an oxygen atom, in the carbon atom, or in the nitrogen atom, or in the hydrogen atom. So if all these things can happen in a very short period of time, it has to be a favored structure. The planar structure is a favored structure for the quickest movement of electrons across various atoms. As you could have seen in the example of benzene and its resonance nature, that leads to a structure that the benzene presently has, unlike a cyclohexane, which is actually a structure where the carbon atoms exist in not the same plane as each other. So a resonance structure generally prefers a planar structure, and hence the same reason extends here too, that electron movement across these various atoms is preferred only by a planar structure. So this plane composed of C alpha of the nth till the C alpha of the n plus 1th residue is called the amide plane, because this can also impose rigidity in the structure, because the carbon atom and the nitrogen atom now exist as if they are a double bond, and hence there is no rotation that is possible across these two bonds, which means there is no rotation in this entire plane, because the C alpha in the nth residue and the C alpha in the n plus 1th residue all are connected to the peptide bond. As these all exist in the same plane, because of the restrictions that the peptide bond puts, the entire plane, the atoms that are there in the entire plane exist as a rigid structure. So what is the importance of this rigidity that the peptide bond brings in, and what is possible otherwise in the other parts of the peptides is what we will see in the subsequent lecture, where we will discuss what is the importance of the rotational freedom across all the bonds that you see right from the left hand side hydrogen to the right hand side OH group. Post peptide bond formation, one can say that the protein gets its characteristic N-terminal and C-terminal locations, because notationally we prefer the N-terminal containing amino acid as the first amino acid. That's why we have represented the residue N, that is the 0th or the first residue, to be an amino terminal, because it contains the NH2 group on its side. But there is a loss of the COOH group on the right hand side, which you have seen in the first slide as an individual amino acid, and similarly there is a loss of the amino group in the left hand side of the N plus 1th residue. Hence the residue that contains the amino group completely, which is the nth residue, is called the amino terminus, and the residue that contains the COOH group, that is the N plus 1th or N plus so on and so forth residue, that the last residue will be called the C terminus of a peptide or a protein. So the peptide bond gives a lot of features that are very characteristic for a protein, and also that are deterministic for a protein in many terms. With this we conclude the second part of the lecture, that is the lecture on the